Okay, so in this talk, we're going to revisit the cut operation on morphisms in the bicategory of Landau-Ginzburg models, with a view of sort of putting everything that we've talked about in previous talks together, and actually, finally, we have all the ingredients we need to state this cut operation on these morphisms. Depending how we're going for time at the end, I might make some more comments about this need to pass to the completion in some circumstances, but if we don't get time, then it will be in the notes. Okay, so as always, let K be a field of characteristic 0. And we're going to consider one morphisms in LG. So where all these things are potentials. Okay, and we're going to need to know the number of variables in this polynomial ring. So we'll denote this polynomial ring in the middle here as a polynomial ring in n variables. Okay, so I guess we need to state all the definitions that we've been using here. So let T be the sequence of partial derivatives of this middle potential V. Oops. And we'll let I be the ideal generated by the elements of the sequence T. And what else do we need? I guess we need the Jacobi ring, which is just the quotient ring here. Okay, and then we recall the cut. I need some names for these. So we'll call this morphism dx and this one y. Recall the cut of x and y is the matrix factorization, which we denote like so. Where the module is this thing. And the differential is just the tensor product. Okay. So in the talk on composition, we showed that we had the composition of x and y, which is just their tensor product over the ring y, is a direct summand of the cut. And our goal for this talk, or our primary goal for this talk, is to show how this composition is a direct summand of the cut. And the way we're gonna do that is to produce an explicit, so we know all the maps involved, strong deformation retract of the following form. Yep. Okay. Okay, so let's do that. So in the previous talk, we showed how to construct this system of T derivatives in the case that T was a Grosvenor basis for the ideal I. So we're going to suppose that is the case now. So suppose T is a Grosvenor basis for I. If this is not the case, more or less the same thing is going to work. We just need to pass to the completion of ky, the iadic completion of ky, rather than working just in ky. And we'll let T1, as usual, through Tn, be the system of T derivatives from last time. It's sort of worth pointing out at this point. So this is actually the only case. So when T is a Grosvenor basis, or maybe some slightly more general cases, some marginally more general cases, this is the only case where we can actually compute. These maps exactly. So in the case of the iadic completion, we can only compute the sort of the versions of these maps by approximating them in the iadic topology. So I suppose that's one reason for working in this special case rather than just passing to the completion every time. Okay, that being said, so again we consider the causal complex. Of the sequence T, and as usual we denote the module like so, where these DTI things are just formal generators. We have, so I guess we're just sort of just recalling a bunch of definitions at this point. We have the connection, right, which is the map on the causal complex given by setting or given as follows, I suppose. Where f is just a polynomial and omega is a product of these DTIs. Okay. And then, so in a previous talk, maybe it was 3 talks ago, we constructed a strong deformation retract. So we showed that the following was a strong deformation retract. So it's the one between the Jacobi ring and the causal complex. And this is, so, sorry, this SDR is over K. And we have that pi is the quotient map in degree 0. And H is equal to this thing. Okay, and sigma is uniquely determined by H. Or I guess rather by Nabla. And you can check the talk for how to compute that. So pi is ky linear, but this is only k linear, and so is this. Okay. So this strong deformation retract is the starting point for our definition of the cut operation. So the next step is to tensor by the module ky x tensor y over ky. And then what we want to do is we want to use our perturbation techniques to mix in the differential. And I kind of brushed over this last time, exactly how we need to do this to mix in the differential. So I think I'll go through it in a bit more detail today. Okay. So let's see. So if we just tensor by ky, then we have this strong deformation retract, which I'm about to write down. So tensoring on the left-hand side just gives us the cut, which is good. And on the right, I suppose I should have maybe said this. I'll just write this down and I'll explain what all the maps involved are. Okay. Okay, so the thing I brushed over before is that when we're tensoring, we're tensoring over ky, right? But only one of these maps is actually ky linear, and the other two are not. So to obtain this new map sigma tilde and h tilde, we do the following, right? We fix a basis. Sorry, I better say what kind of basis. A kxz basis for this thing, x tensor y, of the form EA tensor FB, where EA lives in X and FB lives in Y. And then we define these maps on the basis, right? And define sigma tilde as on the basis as like so. So here R lives in the Jacobi ring. And that's going to be just the effect of applying sigma to R. Okay. And then similarly for H. I'll use G here. So G is an element of the causal complex. Okay, and extend kxz linearly. So this strong deformation retract is over kxz. Okay, and that's the sort of how we get around these maps in the original deformation retract not being ky linear, but being only k linear. Okay. The next step is perturbation. So we're gonna try to mix in the differential of x tensor y. So we're going to treat this thing as a perturbation. So in order to do that, the first thing to do is to show it is small, which I seem to have deleted from my notes. So the reason it is small is, okay, these notes don't make a lot of sense, so I'll fix them up later. Note that the composition of D and H tilde is nilpotent. Since it is has degree -1 with respect to the Z grading on the causal complex. And the causal complex is obviously bounded, right? So eventually this map will be 0. This means that D is small as a perturbation. So we set A, so this is now following the ideas of the perturbation lemma. We set A to be this thing. So if this thing is small, then this inverse that I've written down exists. And in fact, we know it's given by this, right? And it's not hard to check this, and we've also shown this in a previous talk. Okay, and then we can just apply the perturbation lemma. We obtain, I guess, a strong deformation retract over kxz, which is as follows. Okay, so we've just mixed in the differential, I'll call the homotopy H infinity. Okay, and what are these maps given by? Sigma infinity is just given by sigma tilde plus HA sigma tilde, right? We showed that in the perturbation lemma. So pi infinity, according to the perturbation lemma, it is this. That you can show by just calculating that washes out to be just the same thing we had before. And then H infinity is similar. Okay. Okay, cool. So now we're going to just come up with some slightly more convenient notation for, or a more convenient way of expressing these maps. So we'll take a look back at the first board. We can write.
The orb didn't follow you for some reason. I don't know why.
Does it not follow other speakers, or is it just me?
I think this particular set of boards is a bit dicey for the, so it's not you.
Has that come close enough, or is it?
Yeah, that's good now.
Yeah, okay. Okay, so we can write H infinity and sigma infinity as follows. So we can write that as, well, we can write down just the definition. spelling out A there. Okay, and then just by re-indexing everything, this comes out to be this. Okay, and then similarly, we can rewrite H. Oh, this should have a pair of L. Should make a note of that. Yep. Okay. Okay, cool. So now it just remains to remove the differential of the causal complex from the strong deformation retract, which I had up on the previous board. Okay, so in a previous talk, we showed that we have the following isomorphism. Of linear factorizations. I guess here I'm setting Z to be this tensor product. Okay, so now we're actually, so at the time we just showed that there was such an isomorphism, and implicitly in the proof it sort of showed you how to construct the isomorphism. Now we're actually just going to write it down and write down a formula for it. Okay, so I guess recall from a previous talk that Ti acts null homotopically on Z. Okay, so let lambda I be such a homotopy. When we showed that such a thing existed, we also showed how to come up with this. Basically, you just differentiate the entries in a matrix for the differential of dx. So this is something we actually know exactly. And next, note that we've got this canonical isomorphism between the following modules. So we have the causal complex tensored by ky on this side, right? And this thing is isomorphic to what we get when we just pull out the ring ky, I guess, from inside this causal complex module to get something looking like this. Right. So the idea is that this module is just the exterior algebra. Okay, and we're just pulling out that ring ky. And I guess here I'm setting theta I to be equal to dt I. Okay. Okay, so it suffices to just use to work with the right-hand side here. Okay. So now we're going to define the maps in the isomorphism. First of all, let delta be the map, which is just this sum. Right. Recall that theta I star means contraction by theta I. So this is an endomorphism of the causal complex, or rather the module of the causal complex. And then we set this thing, exp of delta, as this. And I'll comment on why this is well defined in a moment. And likewise, exp with minus delta as this thing. Okay.
Will's like, I can't make it, and then 2 seconds later he's there. I will.
I explained in the thing. Yeah, sorry, but I am here now. Are these, can I just ask, have you erased any boards? Maybe it looks like you have.
Yep.
Yeah, that's okay. I'll grab the notes that you have.
You could also just read from the...
So at the moment...
Oh, go ahead.
Yeah, so I guess the important board at the moment is... So on the fourth board, we've got this strong deformation retract, which I'll just put a little blue star next to. We've sort of explained how to come up with that step by step. I think we've covered this a couple of times, but I went into a bit more detail this time. And now our goal is to remove this differential here, this differential of the causal complex.
Is this
we're doing that
still? Is this still for the sake of composition? I feel like we've already done this in this seminar. Are we redoing it?
So this is to come up with a formula for the cut operation. So we've shown such a thing exists, but we haven't come up with formulas. So we're sort of going over old ground, but keeping track of what the formula is for everything.
I see. Okay, cool. Yeah, got it. That's helpful. Thanks.
Yeah. So I guess here we've got, so if you look at the first board, we've got this isomorphism here, which again, we've shown to exist before, right? Where we just removed the causal differential. And now we're writing down a formula for this isomorphism.
Cool. All right, got it.
Okay.
Thanks.
Okay, so we have these two maps here. We've got delta up the top here. We've got x of delta and exp of minus delta, the exponential, I guess, of minus delta. And I need to tell you why these are well defined. So I guess note that delta is nilpotent. Why is that? It has -1. It has degree -1 with respect to the z grading, right? And this module is bounded in negative degree, or it's bounded from below. Okay. So let's prove this is the isomorphism we claim. Okay. So the map x delta going from this thing to this thing. So basically the same thing, but without the... this should be a direct sum here. The same thing, but without the causal differential, is an isomorphism of linear factorizations, of matrix factorizations, I suppose. with inverse. Okay. Okay. So proof. I guess it's clear, or maybe I should say it's an exercise, that exp of delta and exp of minus delta mutually inverse isomorphisms of modules. So really the only thing that we need to do is to show that they commute with the differentials on both sides. Okay, so let's go ahead and do that. Okay, so our first goal is to show the following. For all m greater than 1. Okay. Okay, so proof of claim. For m equals 1, we have, well, that is just this thing. And writing in the definition of delta gives us this. Overloading m here, I guess. Okay, and that, if we remember that the definition of lambda, that thing just comes out to be t, right? Because lambda is a homotopy between ti, lambda I is a homotopy between ti and 0, which just washes out to be dk. Okay, which proves the claim in the case of m equals 1. So for m greater than 1, so first note, we can write, so I'm just going to, I guess, write this, should be n, I think. Oh no, m, yep. So this sum we can split this up like so. So here we're just writing in the definition of the commutator and splitting it up into two separate sums. Okay, and then we can just re-index, right? So we can keep the first one exactly the same. And the second one, we'll make it look like the first one, which involves shifting everything up by 1, just to m, sorry. Okay, and then heaps of stuff cancels out, and we're just left with this commutator. Okay, so now we're going to use that in the proof. So let's continue on the fourth board. So if we, why is this blue? So now we'll just actually
maybe just
write down the commutator.
Pause a second, Rohan, because even I have to think about this for a second. So this is it's the delta to the power of the m minus I in the second last line, right? It's sort of the dot disappeared a little. Is that right?
Here.
No, I just added a dot here.
Oh, sorry. Yes. Yeah.
Okay, so the only terms that survive are the I equals 0 terms, which is dz delta. Oh, okay, I see. And then the only term that survives in the second one is the m term. Wait, what? The m term is... Oh, yeah, okay. Mm-hmm. All right, yep. I got it.
I can help with this as well. So I'm just not seeing how this has proven the claim. So
we haven't finished proving the claim.
Oh, I thought you said that we'd finished it. Now we're going to use it.
No, sorry. Sorry, we're going to use this fact in the proof of the claim.
Okay.
Yep.
Okay, thanks.
Okay. Cool. So let's do that. So now we can just compute the commutator, right? So we can write in the sorry, the definition. Oh, sorry, what we just showed, right? Okay, and then we already computed this thing before in the m equals 1 case, so we can write that in. We showed it was just this. Okay, and then these all commute. The deltas commute with dk. Which gives us, oh, yep, cool. This doesn't involve I, so this just gives us, and there's m terms in the sum, so this just gives us m delta m minus 1 dk. Okay, and that concludes the proof of the claim. Any questions before we continue?
What's the difference between dk and dz? And also, is this right? Do we have dz at the end? Is that dk meant to be dz, or is that dk? Yeah, that doesn't line up with the statement.
Yes, this should be d. Let me. Sorry, I'm wondering whether I stated the claim wrong or I.
Yeah.
I think I stated the claim wrong, right? Because if we look in the m equals 1 case, so I'll go back and just correct on the previous board. I'll just drop it out. Yeah, okay, this is good because this has come directly. Yeah, okay, that should be. Sorry, I just wrote the same thing again. Yeah, so
there's
in the m equals 1 case,
someone sent to Pinter's head.
Yeah, in the m equals 1 case, that's what dk is, right? So it has to be dk. And why does that follow? Yeah, okay, and this all makes sense in that case, right? So I stated the claim wrong. So sorry about that.
Sorry.
Yeah, and so what's the difference between dk and dz? Yeah. So dk is so I guess there's two things going on here. We've got the causal complex of the sequence T. So the sequence T is, I don't think you would have seen that. That's the sequence of partial derivatives of a potential V. And we've got the matrix factorization Z, which is just the tensor product of two matrix factorizations, or rather the composition of two matrix factorizations. Okay. And we've tensored these two things together. So we've got the differential dk plus dz on one side, and just we're trying to get rid of that. So we've got just the differential dz on the other side. So the goal is to sort of remove this this differential from the strong deformation retract which we're working with.
Cool. Yeah, got it.
Cool.
Thanks.
Okay. So now we just compute the commutator. So at the moment we're trying to show that it's a morphism of matrix factorization. So in other words, it needs to commute with the differential. So the way we're going to do that is just to first of all compute the commutator of, no, not that, of this. Okay. Well, that is, remembering this sum is actually finite, is this. Yep. And then we just write in what we use our claim, I suppose. The m cancels with one of the m's on the bottom, leaving us with m minus 1 factorial on the bottom. And we have delta to the m minus 1 and the dk remaining. And re-indexing, this is just the same thing as exp of delta dk. Okay. Now, this thing here, okay, this is where I need to make sure I get the signs right. This thing here is dz exp of delta minus exp of delta dz.
The suspense. Was he going to get it minus?
Yeah, no, that's correct. Yep. Yep. So yes, because everything is, yes, that's how it works out, because the commutator is graded. And then we can rearrange this expression to get what we want, which is exp of delta dz plus dk equal to dz exp of delta, right? So in other words, it commutes with with the differential. So we claimed on, if we look at the statement of the lemma, we claimed it was a morphism from something with the differential dk plus dz on one side, and just the and then to something with just the differential dz on the other side. And what we've shown is that this satisfies the property that it needs to be a morphism of linear factorization of those particular linear factorizations. So this proves the lemma. Okay. Any questions about that so far? Great. So now we can put this all together. So let's go take another look at board number 1. Okay, so what we've done is we've constructed, so if we put everything together, a strong deformation retract over kxz as follows, right? So we have the cut on one side. I'll tell you what these morphisms are in just a second. And on the other side, we have this. Okay, where we have capital phi as exp of delta alpha, where alpha is, did I rub that off? Yep. So alpha is just the isomorphism, the canonical isomorphism, which removes the ring K, which pulls the ring KXY out of the out from inside the wedge, sorry, the exterior algebra, and sigma infinity, which is the thing we had before. And then we just put everything back on the other side, right? So just conjugating with these isomorphisms. Phi prime is similar. Hang on, what have I done here? Okay, and then H is the same thing again. Where H infinity is as before. Okay, so this is it. This is the complete fully explicit isomorphism, or sorry, the complete map between the cut operation and something, or the cut and something that has the composition as a direct summand. Yeah, I suppose that's all. I guess we don't really have too much time to talk about the issue of going to the completion, but it's in the notes. And yeah, are there any questions about this?
So you said it's the map between the cut and the thing with the composition as a direct summand. What?
Yep.
Why did you correct yourself from isomorphism? So this is the deformation retract, but not an isomorphism. Is that the point?
Yeah. Well, it's an isomorphism in the homotopy category. I suppose I don't want to just say isomorphism unqualified, because it's not an isomorphism not in the homotopy category.
Yeah, sure.
But I guess, yeah, it's not wrong to say it's an isomorphism if you're talking about the homotopy category.
And what do you mean by going to the completion? When does the completion come in?
Yeah, okay. So at the
start... Do you mean the algebraic completion? You're going to take the completion of one of these rings or something? Okay.
Yeah, so we look at the iadic, so I being the ideal generated by the elements of the sequence T. Oops. Completion of KY. And the reason for doing this is in order to come up with our system of T derivatives, which we use to come up with our connection, which we use to come up with this thing here. So this thing here is decay nabla inverse nabla. We needed to assume that T was a Grosvenor basis for its ideal, which is obviously not true in general. It's a good setting to work in if you want to come up with examples. But in general, to get around, so you sort of do things in a very similar way, but to get around the way of dealing with it, if T is not a Grosvenor basis for its ideal, is to pass the completion, the iadic completion of KY. And yeah, it's sort of, everything works in exactly the same way, except you have to be in the completion, which is maybe a little annoying. Yeah.
All right. Right. So this map only exists. I don't understand it. So this map only exists in the case where the sequence of partial derivatives is a Grosvenor basis, or is it that it only has certain properties in that case?
I guess it's that it only exists. So I guess we always have. So this isn't how I've defined these maps before, but I'm going to write it like this. We always have a map that works in a pretty similar way to these del TIs on the completion, right? It has essentially the same properties. If T is not a Grosvenor basis, then we may have that the image of this map, when restricted to K and I, sitting inside the completion, is not this, right? Is not KY again, right? When T is a Grosvenor basis, and actually under some, so in my thesis, I prove it in a slightly more general setting than just T being a Grosvenor basis. And you can also come up with specific examples that don't have that necessary condition, but it's again not necessary to pass to the completion. That you do have this equality here. So these maps, actually, you can think about them as just being maps on the original polynomial ring. But you can also come up with examples where you genuinely do need the completion. And sometimes you need it really badly, like you need it for almost every single element of the polynomial ring. Will not end up staying inside the polynomial ring when you do this mapping.
Okay. Cool. So in the case where T is not T, but the wait, so what what, like, this doesn't happen often, right? Like, surely you don't need to go to the completion with the majority of the standard examples of potentials you would be interested in, right?
Yeah, I'm not certain. So, like, lots of nice stuff. In lots of nice stuff, T is a Grosvenor basis. So, for example, I looked at like, if you look at like the isolated singularities of curves, all of them, T is actually just a Grosvenor basis itself for its idea, or at least, you know, some nice form of that. With the ADE singularities of surfaces, E7 and DN T fails to be a Grosvenor basis. But I think you can prove that passing to the completion is still not necessary, although it doesn't fit within the necessary condition I've stated. It needs a more, you know, tailored argument for that to work. Whether or not whether or not we need to pass to the completion basically boils down to whether some algorithm, which I state in my thesis, terminates. So that's sort of how I'm proving that things don't need to pass to the completion or do need to pass to the completion, whether this algorithm terminates.
That algorithm terminates.
Inputs, you know.
Right, okay.
Because, yeah, the algorithm is just generating the coefficients of a particular series expansion in the I-adic completion. And if you can prove that series expansion is finite, then you can just work in the base polynomial ring.
So,
but yeah, I don't know about in general, right? Like maybe, you know, if you just want to take in some arbitrary potential, maybe there's a very good chance it's not a Grosvenor basis, right?
So what happens if you just take your potential, you take your sequence of partial derivatives, and then you extend that to a Grosvenor basis for the same ideal? Is the point there that you've now changed the sequence that you're looking at, and so it's not even relevant necessarily to the original potential that you were interested in?
Yeah, I guess, yeah, so you could change the sequence and get, so why would that not work? So one reason that might not work is the new sequence. So we used it in the lemma just then. We had that the TI acts null homotopically on the matrix factorization Z. So it's possible those new ones don't end up acting null homotopically.
Well, they generate the same ideal. So the things that act null homotopically form an ideal. So that won't be a problem. But the point is the Grosvenor basis may be not quasi-regular, right?
Yeah. So that's the main problem, right? It might not be causal regular, which is a big problem if that's not causal regular.
Right. You could start with five partial derivatives and then get 100 things in your Grosvenor basis, in a minimal Grosvenor basis. So.
Okay. Nice. Thanks. Good talk.
Yeah. Thanks, Ron. Before you guys go, there's a special treat tonight. This way.
Uh-oh.
No, it's not dangerous. It's not going to kill you.
I don't know if I believe
you. You'll have to...
Oh.
There you are. This is the...
Yeah, there we go.
This is the thing from the other world. So this is Will's music, Rohan.
Yeah.
Yeah, cool. That's really awesome.
Yeah, this is like one of the songs. I played this.
Yeah, I should put some way up the tree. Nice.